Welcome back to the deep dive. Today we're doing something a little different. We're focusing our entire analysis on just one single, highly specialized piece of equipment.
That's right. The NTI E-PST100IS, Intrinsically Safe Pressure Sensor Transmitter.
It's definitely deep in the weeds of industrial engineering. But our mission here is to sort of cut through that jargon and figure out the incredibly high-stakes world this thing is built for.
And when you look at the source material, one phrase really defines the entire device: explosive atmospheres with barrier.
Right. So this isn't just a gauge you screw into a pipe.
Not at all. It's a critical safety component.
Okay, so let's start with that key phrase you see everywhere, intrinsically safe. I mean, what does that actually mean in this context?
It means the device is engineered from the ground up so that it can't release enough energy, either thermal or electrical, to ignite a flammable gas mixture.
So it can't create a spark.
Exactly. Not during normal operation, not during a short circuit, not even if the thing is completely destroyed. It's fundamentally, inert from an energy perspective.
No. Which brings us right to its core rating. The E-PST100IS is for hazardous areas, Class 1, Division 1.
And that's the key. Class 1 Division 1 means those flammable gases or vapors. They aren't just a possibility, they're present under normal operating conditions.
So the air itself is basically ready to explode. And that brings us to the price. Part number E-PST100IS, it's listed at $2,600.
Right. And that price tells the whole story, doesn't it?
It says this is not a normal component. Its main job isn't even measuring pressure. It's preventing a catastrophe.
That's it, exactly. Its secondary function is measuring pressure.
Okay, but here's something that confused me in the specs. If the sensor itself is intrinsically safe, why does it require a separate NTI E-PST100IS, intrinsically safe barrier to work in those locations? Isn't that redundant?
That's a great question. It's not redundant at all. Think of the barrier as like a firewall, but for energy.
A firewall for energy,
Right.
okay.
The sensor is designed to only handle a tiny safe amount of power. But the control system it's connected to, outside the hazardous zone, could fail and send a huge surge down the wire. The barrier, which costs $810 on its own, is a gatekeeper.
So it guarantees that no matter what happens upstream, only a safe trickle of energy can ever reach the sensor.
Precisely. It isolates the hazardous area from the non-hazardous. It's a complete system.
That makes perfect sense. We've handled the electrical side. What about the physical engineering? The housing, the connection itself?
Well, the sources point right to the material. The process connection, the part that screws into the system, is made of 316 stainless steel.
Which is important because corrosion.
Exactly. In these high-pressure, often corrosive environments, a lesser metal would weaken. If that connection fails, you get a catastrophic release. That failure itself could generate a spark. So 316 stainless is a non-negotiable insurance policy.
The level of detail here is just incredible. I also saw a spec for a maximum cable length, 1,000 feet or 305 meters. Why would that matter? Why limit the cable length?
It all comes back to that same principle of limiting energy. Even a simple wire has properties like capacitance and resistance.
Right.
Over a long enough distance, a cable could theoretically store enough electrical energy to release it as an ignition-causing spark. That 1,000-foot limit is an engineered safety cap. It ensures the entire circuit, including the wire, stays within that certified safe energy threshold.
So if you're listening to this, I think the core takeaway is pretty clear. In critical infrastructure, a device like a pressure sensor is, well, it's rarely just a pressure sensor. It's a key piece in preventing a disaster.
It really is. And the whole concept of intrinsic safety and these barriers, it shows you how safety engineering is all about managing and eliminating energy sources. It's not always about the flashy device doing the measuring. Often it's the quiet, unassuming component, like that $800 barrier.
That's a great final thought.
It really makes you wonder, doesn't it? As you look at any complex system, what's more important to its safety? The device that's measuring something or the device that's controlling its energy?